So that part was pretty. The part before was fairly heavy and it's kind of deep, but really to kind of do calculus, we just need to make sure we understand the two basic points. So the derivative and the antiderivative undo each other; they are opposites. And secondly, the area under the curve is the displacement on the antiderivative, and vice versa. So let's just practice doing that. Let's just use this, the antiderivative, to find the area under the curve. Okay, so instead of calculating this area by using Riemann sums and a whole bunch of little Riemann sums, we're actually going to calculate just using an antiderivative. So I can anti-differentiate this and say that the area under the curve relates to the antiderivative 9x squared over 2 minus x squared over 4, and the displacement from 3 to 0. That displacement works out to be 81 over 2 minus 81 over 4, which is 81 over 4 units squared. So this area is 20.25 units squared. Okay? So the area under the curve, this area, can be calculated using a displacement on the antiderivative. So same thing here. So if I have to sketch this graph, okay, we've got a bounce at 0. It looks like a 0 at positive 2, so it kind of bounces like this, goes through, and we're being asked to find this area from 2 to 3. Okay, so we want to use the displacement on the antiderivative to calculate that area, because we know that they relate to each other. So again, the antiderivative and then we're going to calculate that antiderivative, the displacement from 2 to 3. Plugging in, I get 81 over 4 minus 54 over 3, okay, minus, that's going to be 16 over 4, which is 4, and 16 over 3. Okay, so actually I should have kept that as 16 over 4. So then I end up with 65 over 4. It's going to be plus 16 over 3, so that's going to be minus 38 over 3. Get a common denominator and add those together, or subtract those. 65 over 4 minus 38 over 3. Okay, I'm going to get 43 over 12, I think, okay, as my area. So the net area works out to be 43 over 12 units squared. Okay, so again, I'm using the displacement on this antiderivative function and saying that that displacement is equivalent to that area under there, because everything that we've done so far points to the fact that the area, even the units of this area, relate to this antiderivative. Okay, so this next one here, so we want to graph this e to the x function from 0 to 3. Okay, we want to find this area, so we anti-differentiate 2e to the 2x divided by 2, okay, because of that k value of 2. We anti-differentiate this, we're going to end up with e to the 6 minus e to the 0, okay, and that works out to be, as a decimal value, I think it's quite big, e to the 6 is going to be a big number. Okay, e to the 0 is 1, so we end up with 402.4 units squared of area. Okay? That y coordinate at x equals 3 is actually quite high. So again, we're just using that antiderivative to find the area underneath that curve. Okay, so for this one here, the derivative is secant squared, so we know the antiderivative must be a tan function. So it's going to be 2 tan 2x. We want to divide by that extra 2 here, and we want to know the displacement from 0.5, from 0 to 0.5. Okay, those 2's cancel out, so we end up with tan 1 minus tan 2 times 0 is 0. Well, that's 0. So our displacement works out to be tan of 1, whatever that works out to be. Okay, if I type that into my calculator, tan 1 is 1.56 approximately. So the slope of 1 radian is the slope of approximately 1.56, and that represents the area underneath this curve from 0 to 0.5. So there are some properties to the definite integral, and they basically follow derivative properties. So if we have a constant in integration, we don't differentiate constants, so we don't integrate constants. I can differentiate functions separately if they're separated by plus or minus, so I can integrate them independently with a plus or minus. This one's kind of important in that if we, the next one. This one is fairly straightforward. If I integrate from A to B, well, it's the same area, so integration is going to calculate that area. So it's the same area if I go from A to C and stop there, and then start from C and finish off at B and add those two areas together. It's the same as the total area integrating right through from A to B. Okay, so that's pretty straightforward. This one here kind of has some important implications later on. But it's a fairly simple idea in that if I'm integrating from A to B, right? So if I'm integrating left to right, I'm going to have an opposite area if I integrate from B to A or right to left. And algebraically, it's fairly easy to justify because if I go big F of B minus big F of A, so I'll put my B and A in there. Okay, so I'm going to get some kind of calculation there. Now, if I switch my bounds, notice I get I'll have big F A minus big F B. So if I plug in my A's and B's in here, here's A here and B here. It's just switching those bounds is switching the subtraction. Well, when I switch subtraction, I'm just going to get the same number or the same area, but I'm going to get an opposite sign on that area. Okay, so this area just is the opposite sign. Okay, well, that makes perfect sense. Where this also shows up is this. Okay, now this is a little bit harder to kind of understand, but if I go from A to B, if I go in this direction, my area above the curve is positive. If I go from B to A, if I go in this direction, that area ends up being negative. Although it's above the curve, it's negative. And try to understand it this way. If I start at time 0 and gain some distance, if I go backwards in time, I'm going to lose that distance. So that area should be negative. Okay, so when we integrate left to right, area above is positive, area below is negative. Right to left, the opposite occurs. Okay, so we're not going to get into that too much right now, but that will show up a little bit later on. I've also added a link here, so try out that link, okay, with the Desmos app, okay, and it'll give you a good idea to kind of help visualize what's happening when we're talking about areas under curves.